Thank you, Paul. Good morning and good afternoon to everyone, wherever you are. I am Rama Rao. As Paul said, I work for an institute called Central Research Institute for Dryland Agriculture. I am going to talk about our recent paper, Climate Change Risk Assessment for Adaptation Planning in Indian Agriculture. Our organization is actually belonging to Indian Council of Agriculture Research. So it comes under the Ministry of Agriculture and Farmers Welfare of Government of India. And we are mandated to lead and coordinate research for sustainable rainfed agriculture and as well as climate resilient agriculture in our country. So there is a project going on called National Innovations in Climate Resilient Agriculture. This work is a part of that project. Just to introduce the topic, Indian agriculture has come a long way since our independence in 1947. We transformed our country from a food deficit country to food exporting country now. But this transformation is a teamwork of many different agencies related to policy making, technology development, infrastructure development, and so on, and also the hard work of farmers. But newer challenges to sustainable agriculture and livelihoods are emerging, and climate change is one of those challenges which actually interacts with and compounds all the challenges, making adaptation an immediate need, but as well as challenging too. Why did we start with this study actually? Given our country's development stage, adaptation is an immediate need for us. Many people are dependent on agriculture for livelihoods. Also, with the country's population, like we account for 17% of global population. So food security is of a very important issue for us. So adaptation is an immediate necessity. But as you know, unlike mitigation, adaptation is context specific and location specific. But our agriculture is too diverse to develop any technology which fits for every region in the country. So this diversity actually makes adaptation more challenging. It requires targeting and prioritization. But in our country, district is the administration unit where most of the development planning and resource allocation happens. So we chose this as a scale for our analysis with the objective, which are the districts that are more at risk of climate change and what are the underlying causes for that risk. So this is the motivation for our study. Just before going to other things, just I want to expose you to what Indian agriculture is all about. One is our agriculture is dominantly by small and marginal fragments. 86% of our holdings are less than 2 hectares in size. That is just 20,000 square meters. And our average farm size is about just 1 hectare. But even more problematic for us is actually each holding on an average contains 1.6 fragments. That means every farmer has his land at 2 different places. And we have huge agroclimatic diversity as well as socioeconomic diversity. We have 15 agroclimatic zones in the country. We have arid climate in the northwestern parts of the country and perihumid climate in the northeastern parts of the country. We have very fertile lands in the northern part of the country, which are popularly known as Indo-Gangetic plains. But our central India, southern India, more drier regions, semi-arid regions with very harsh environments. So we have huge diversity in terms of agriculture. So the technologies or adaptation technologies or adaptation options should match these varying conditions. And nearly half of our agriculture area doesn't have access to irrigation. So mostly it is dependent on rainfall, which is actually seasonal in nature. A lot of rainfall happens just during 4 months, June to September. So after that, largely a dry period. So we have to do our agriculture with the rainwater that we get in those 4 months. Our farmers are largely subsistent oriented, though some market orientation is increasing the last about 10-15 years. Largely, our adaptive capacity of our farmers is low. They have not many resources, low investment capacity, inadequate access to information, technology, and capital. But of late, we are observing increasing feminization of agriculture in some areas because male members of the family are migrating to urban areas. So the agriculture is left to be operated by or owned by female members of household. We adapted the risk framework as given in the IPCC's assessment report 5, where risk is viewed as a function of hazard, exposure, and vulnerability. As you know, the whole system operates in a broader context where climate and socio-economic processes interact with each other, depending on the population growth, technology development, what adaptation and mitigation actions take place, and governance structures. They together determine all these hazards, exposure, and vulnerability. And risk is a resultant of interaction between these three: hazard, exposure, and vulnerability. That's what we showed on the right-hand diagram also, where we show that vulnerability, exposure, and hazard together determine risk. These are just definitions of this terminology given by again IPCC. The vulnerability is a kind of predisposition to be adversely affected. The exposure is who and what are getting exposed to the hazards, or in this case climate change and manifestations. And hazard is actually how climate change manifests in terms of physical events, extreme events, all those things. And risk is actually a potential consequence of disease, population, or systems that are exposed to climate hazard. And depending on the vulnerability, the risk results. So this is the whole process that we undertook. So there are different methods of risk assessment, but in this case, we followed what is called indicator method. So first we start with selecting indicators relevant to each of these three components of risk: hazard, exposure, and vulnerability. And then we normalize them to make them comparable or unitless. And then with the weights obtained from the experts through budget allocation method, we aggregated them into indices of vulnerability, exposure, and hazard. Then we rescaled them, and finally we constructed the risk index. Based on that, we divided all the districts in the country into different grades of risk or intensities of risk. For this estimating hazard indicators, we took CMIP 5 based climate projections. We took an ensemble of 30 GCMs of CMIP 5 group, where we downscaled the data at 0.5 by 0.5 degrees resolution. We corrected monthly bias corrected. We did using hybrid delta method, and we used the data on maximum temperature, minimum temperature, and rainfall, RCP 4.5 scenario. So we regraded and realigned the data with. We have our own organization of meteorology, India Meteorological Department. They provide data at a different grids. So we had to regrid and realign the grids with the GCM grids and IMD grids. Then we constructed an ensemble mean for 30 models following probabilistic averaging method. So finally, we got the district level estimates from the grid level estimates by overlaying the Thyssen polygons on the district boundaries, and then we took a weighted average of values of those temperature and rainfall value. And we took these values for baseline 1976 to 2005 and also projection 2022-49. So based on using these values, we constructed our indicators that are relevant for planning in agriculture. So these are the list of indicators that we selected for constructing these indicators of vulnerability, exposure, and hazard. Hazard, we took a looked at both historical hazard in terms of cyclone, flood, and drought, and future hazard. As I said, using the RCP 4.5 projections, we worked out the change in the 2049 over 76 to 2005 in these different indicators. So we followed two normalization methods. The first one is popular method, that's score normalization. The second one is actually we postulated this method so that when we are dealing with the change kind of indicators, we wanted to retain the sign of the change in the direction, sign of the change. So if it is a positive change, we wanted to retain the positive change. If it is negative change, we wanted to retain the negative change. So we came out with this kind of normalization method. So these are the results. These are some of the exposure indicators. I'm not showing all the indicators, some example indicators I'm showing. So this is net sown area, which means actually the cropped area in the country as a proportion to geographical area in each district. You can see all the dark pink districts where most of the geographical area is actually sown to some crop. Similarly, the percent of small and marginal farmers, you can see most of the country It's a pink color, so you can see more than 60% of our farmers are small and marginal in terms of farm size. Then vulnerability indicators, one is annual mean rainfall. For that period, 76%, you can see the distribution across space and irrigated area, and also groundwater availability. Actually, more than half of irrigation is dependent on groundwater, which is also rain dependent. So groundwater is an important resource for our farmers to protect their crops and to get good yields. That's why we took this one of the indicators. Also available water holding capacity of soil, how much moisture the soil can hold. So this is an indicator that can that soil can support. And then vulnerability per capita income in each district, and also income inequity or income gap. That is another indicator that we chose. Coming to historical hazard indicators, basically looked at three extremes. One is drought, the second is cyclone, and the other is flood proneness. In terms of future hazard indicators, actually we were looking at changes with respect to the baseline. So one is change in maximum temperature. The second is change in the minimum temperature, that is night temperature. You can see the distribution range of changes. Also, the third one is number of hot days, which is actually more 4 degrees higher than the days normal during that particular period. And also cold days, extremely cold days, like less than the normal by 4 degrees centigrade. These are other rainfall related indicators. In our country, as I said, the rainfall season, monsoon season starts in June. So June and July are very crucial for agricultural planning. That's why we looked at the changes in possible changes in rainfall during those 2 months, so that agricultural planning, it will have some implications to agricultural planning as well as adaptation planning. Similarly, drought and dry spells. Drought is actually rainfall deficit by certain percentage, and dry spells are actually rainless period during crop growing season. So how long the dry spells are, and also extreme event, maximum rainfall as percent to annual rainfall. So extreme rainfall events will have also implications for planning agriculture. And then we constructed using the weights. So these are the weighted sums of the indicators included in each of those components of risk. You can see where the exposure is high in the northern parts of the country. These are the states where the exposure is very high, because one of the reasons is population density. In some places, the cross-fed cattle are very high in number. In some places, small and marginal farmers are also very high number. And then vulnerability, you can see the northwestern parts of the country and central parts of the country, the vulnerability is high. And historical hazard, both coast and coastal region, east coast as well as the west coast, southern west coast, and also northwestern parts of the country, historical hazard is here higher. And future hazard, you can see most parts of the country, central, eastern and northern and northeastern parts of the country, you can see very high future hazard. So this means actually temperatures are going to rise, rainfall is going to decrease, and hot days are going to increase, which is not good for agriculture. And then we finally constructed the risk index. We can see the distribution of risk districts based on the risk. We identified 310 districts which are having either high risk or very high risk out of 573 districts that we did the analysis. And for these 310 districts, we also identified which one is the component that is contributing most to risk. You can see that in some districts, exposure is actually major driver of risk. And in some districts in northwestern parts of the country and central parts of the country, vulnerability is the major driver of risk. Because we have to target, depending on the driver of risk, we have to target the interventions, we have to prioritize our interventions and investments. So this is the distribution of districts based on the risk across different states of the country. Then adaptation options in terms of, because when historical hazard, that is, this is a combination of hazard, drought, flood and cyclone, what should we do to deal with this? So we need mix of technological and institutional policy options. And also we need incremental adaptation as well as transformative adaptation. Similarly, for future hazard, where the temperature is going to rise, rainfall is going to change. So we need a mix of investments. We need actually investments in research and development. We have to strengthen our institutions to work together and also we need transformative adaptation. Similarly, for exposure, it's most difficult to deal with, so we have to reduce dependence on agriculture by taking away people from agriculture through industrialization and all the other things. And also vulnerability is also we have to reduce vulnerability by increasing groundwater, by increasing incomes of the farmers. We also should address some of the social issues. We have to address actually development deficit that country still have to address. Again,
Rama, you've got like 3 minutes.
Thank you. I'll finish in 2 minutes, 3 minutes. So within each component of risk also, we have other drivers. Suppose in historical hazard, there are 3 drivers, and future hazard, these are the important drivers of risk. Increase in maximum temperature, increase in minimum temperature, and increasing drought and extreme rainfall. So our whatever intervention that we plan, they should address these kind of hazards. Similarly, exposure and vulnerability. So these are the issues that we have to grapple with if we want to reduce the risk. So similarly, what we should do for this drought, flood, and cyclone. So we listed some of the possible intervention that will help us in addressing these kind of issues towards reducing climate change risk in the country. So summing up, climate change is a reality and it's a potential threat to sustainable agriculture in our country. Risk assessment is an important initial step in adaptation. But this assessment identified districts with high climate change risk as well as the underlying drivers of that risk. So adaptation planning has to address the drivers of risk and come up with suitable interventions that address those drivers. And we have to prioritize districts where the climate change risk is high, given the limited resources we have. And climate change risk better managed through vulnerability reduction because of the uncertainties associated with climate change projections, and as well as the difficulties in dealing with reducing the exposure component of risk. But we did this analysis using only for one RCP for CMIP 5. So, and also we have to remember the uncertainties of projections which are to be factored in decision making. But we didn't stop here. We are continuing work. This is a sectoral assessment, but now we are going towards commodity specific risk assessment at a more granular scale at 0.5 degrees by 0.5 degree. So we are trying to identify hazard specific, commodity specific hazard using CMIP 6 projections. And towards this, we started a project called Atlas of Climate Adaptation in South Asian Agriculture. So where we are working with VISA Summit, that is International Center for Maize and Wheat Development, and the National Agricultural Research Systems of Bangladesh, India, Nepal, and Sri Lanka. We are working together. So we are now 2 years into this project. So very soon we are going to launch this website in a couple of months. This is still under development, where we are trying to work out granular scale climate risk at half degree by half degree spatial resolution using CMIP 6 projections, using the data from Climate Hazard Center of California and also CMIP Center. So we are using 2 scenarios of CMIP 6, SSP 2.45 and SSP 5.855. That's all I have. Thank you. I hope I am in time.